everyone. We shall continue our discussion on thermal stresses. I shall extend the thermal stresses for what are called as compound bars and composite bars. So we all know what is meant by thermal stresses. Okay, stresses induced because of the change in the temperature of a body. Okay, so are known as thermal stresses. Then what is meant by compound bar or composite bar? The other day in my previous class also I mentioned compound bar. So it is basically a bar, compound bar or composite bar, both of them are one and the same. It is basically a bar. Bar is a long member having a smaller cross-sectional dimension subjected to axial load. Okay. So here also the load is going to be the axial load, but it is made up of not only one material, it is made up of more than one material. In that case we call it as a compound bar. Compound bar is a bar which is made up of more than one material. Okay, then what is the special case? Okay, we are going to discuss compound bars subjected to various loads also. Maybe separately I shall take up. Now today I shall discuss compound bars subjected to thermal stresses. Let us consider a general analysis, and then I shall apply that by picking the few problems from appeared in the examination. Okay, let me take a bar, a compound bar made up of two materials. So this is one material. So what is this? This is say a bar like is having say circular cross section. It may be a plate like thing also, doesn't matter. Let me call this as this is a one material one, and whose say I know what is the area of cross section of this, and I also know what is the Young's modulus of elasticity of this, and I also know what is called as the alpha 1 of this, the coefficient of linear expansion of the material made up of this bar, this portion of the bar. Okay. Then surrounding this I have another. Okay, maybe I have a hollow bar, so whose inner diameter exactly matches with the inside one, number one. Okay, this, the outside one, this is what? Okay, you have something like this now. Okay, this is the outside diameter, this is the inside diameter. Okay, this portion I call it as number 2. Okay, material number 1, material number 2. Okay, so both of them are circular in nature. So I have information about what is A2. So what is A2? Pi by 4 into if I call this as D2 and this as D1. Pi by 4 into D2 square minus D1 square. That will give you what is the cross sectional area of this portion. Similarly, okay, I know what is called as E2, Young's modulus of elasticity of this material. The material, this material and this material, both of them are different. And this is the alpha T. Okay, the material has a coefficient of linear expansion, alpha T. So all this, and I know what is the length of this bar. Okay. So let me assume that this is the length of the bar. Let me call it as L. And this is at a temperature T. At a temperature T, its length is L, and okay, and it is perfectly alright. Okay, now, so how did they join, etc.? We are not going into the details of that. How this kind of bar is made, then how they are attached between the two, etc. All that is immaterial. Probably I may have exactly one collar here and one collar here, which make them attached. Okay, all that. So now the whole unit right now is one unit for me. Please remember, this kind of bar I am going to use it not only at temperature T, I may use it at some other temperature, much more than T or much less than T. So let me assume that when the temperature changes, then its length may increase, no problem. Its length may increase, but the outside one and the inside one, both materials, both portions have to undergo the same extension. So if the temperature increases, now say T plus delta T, so what ultimately is this portion may become something like this. So what I mean is the outside one and the inside one must undergo the same amount of extension. This is what I want and this is what is going to be, shall happen. Okay, so if we have, then how does it happen? So I know that this is alpha 1 and this is alpha 2, and when the temperature changes they undergo a different amount of extension. But then how do they have the same length? They are all friends, the materials are friends, they are not like India, Pakistan. They have their own understanding, they will have a compromise, and of course when the temperature changes and they have the same extension, then each portion of them, they are subjected to stresses. And what are those stresses? That's what we want to calculate. What are the thermal stresses induced? So due to the change in the temperature, the whole unit will undergo the same amount of extension. Okay, so for this I shall go step by step. Okay, so what might have happened, that's what I shall analyze it. Okay, this is what the method of analysis, the steps, whatever I indicate, that will not happen in the real bar. It is only for our understanding. Okay, what may happen. Finally, the whole thing, when the temperature changes, the whole unit will undergo a different change in length, and in the course of that, they are subjected to stresses. Okay, now let me explain how to calculate those stresses. For that purpose, I am showing it. Okay, there is material 1 and material 2, and both of them have different alphas, therefore, and they are subjected to what are called as the different amount of free expansion. Okay, so what is that delta 1, L1, I shall call it as delta L of 1, it is not delta L1, delta L of material 1. Okay, I would like to calculate this. How do you calculate? Quite simple. The same basic concept what we have understood, alpha 1 into L1. L1 is same as L. L1 is, they are not having different length, the same length, alpha 1 into L into delta T. So this is sum of value, so many millimeters. So little later, what I am going to have, if I take the question from the examination, they will have some numerical values, nothing else. It is exactly the general procedure of this. Okay, now for our own analysis, I shall assume that alpha 1 is greater than alpha 2. Okay, only 5. Why? Okay, just for the sake, you can have the other way also. So what I mean is, similarly when I calculate delta L of 2, if I calculate alpha 2 into L into delta T, this also is millimeter. Since alpha 1 is more than alpha 2, delta L1 is more than delta L2. Okay, they are more, but not much difference actually. We are talking alpha 1, it is something into 10 raised to minus 6. So, but compared to these two values, there is some gap. Okay, so for our understanding, I shall show as if that gap is quite large, only for the sake of understanding. Okay, you all agree that alpha 1 is more, and therefore delta L of 1 is more than delta L of 2. Okay, let me show that delta L of 1. Okay, when the temperature changes to T plus delta T, and the inside bar will undergo a change in length. Okay, as I said, only for the sake of understanding, I am making it, showing it as if it is very, very large. It is fraction of millimeter also. So what is this length? From here to here. What is this length? This is the free expansion of the material number 1, and this is delta L of 1. Okay, fine. Then what about the second one, the outside one? Outside one also will undergo expansion, delta L of 2, which is given by this, and that value, and you know that delta L of 2 is smaller than delta L of 1. And let me assume that it is something here. This value is, what is this? Delta L of 2. Okay, if they are allowed to undergo free expansion and it is not compound bar, and this is what is going to happen. As the temperature changes, the inside one will undergo larger extension and the outside one will undergo smaller extension, and this is how it becomes like this. As I told you earlier, the compound bar shall have the length, the same length for inside and outside, irrespective of the temperature, and therefore they are not going to be like this. They are friends, they will have compromise, they will have a discussion. Okay, the material 2 says I can go only up to here, material 1 says I go up to here, and they have discussion and they have a compromise. What is that compromise? The inside one, I am ready to compromise and I shall reduce my expansion. And material 2 says I shall also ready to undergo little more expansion and they shall have a compromise, say somewhere here. So finally they will come up to here. The inside one will compress and comes up to here, and the outside one expands and little more and comes up to here, so that the length of the entire compound bar will remain same. Okay, how does it happen? For that to happen, if this has to, okay, the final position of this end, okay, then the inside one has to undergo a compression, because it has undergone expansion up to here, then it has to undergo a compression. That means it has to be subjected to a force. Okay, let me call that this is the force P. And similarly, and this also must undergo expansion, and this also must be subjected to a force. And it can't be a different force, because the whole thing in mechanics of materials, I keep telling, always we have equilibrium. This force and this force, please remember the force I am showing here is acting on this portion, on the outside bar. Okay, that is also must be equal to P. This P is responsible for the extension up to here, and this P is responsible for the compression up to here. Okay, and all this length is very small. Okay, this extension, all that, and whenever I say the length of the bar, I shall go back and say that L is the length of the bar. Okay, so now I hope you have understood. The inside bar is subjected to a force, compressive force P, which will bring this end here, and the outside portion of the bar is subjected to a tensile force P, which will bring it and this edge to here, so that this will be the final position of the bar. Okay, so now what is this portion? Can I write down how much is this portion? Okay, so this is basically extension because of the tensile force. This is nothing but P into length. What is the length? Length is L divided by area. Area of what? This is the force which is acting on the outside bar. That is nothing but A1 divided by Young's modulus of elasticity E1. PL divided by A1 E1. Sorry, not A1. It is outside. No, outside is A2 and E2. PL divided by A2 E2. Similarly, how much is this portion? This is equal to PL divided by A1 P1. PL divided by A1 P1. Make use of this entire thing. Now write down the equation. What is that equation? From here to here. From here to here. How much is that? That is delta L of 1, which I already know. Delta L of 1. That is nothing but this length. Okay, so from that I shall start from here to here. That is nothing but this length from here to here. What is that? That is equal to delta L of 2, which also I know. Okay, this plus this length, what is that? P L divided by A2 E2. Okay, so I started from here and this plus this plus this. That is equal to plus P into L divided by A1 E1. So check what all things you know. You know delta L of 1. You know delta L of 2. You know all other things except P. You know L, you know A2, you know E2, L, A1, E1. All the things are known. From this expression you will find out what is the value of P. So many Newton. Okay, then if you want to find out what is stress in material number 1, stress in material number 1, that is nothing but P divided by A1. This is so many Newton per millimeter square, and inside bracket write down what is the nature of the stress. What is the nature of the stress in the material 1? It has to be compressive, as you can easily see here. And similarly, what is the stress in sigma 2 in the material 2? That also is subjected to P divided by A2. This also is so many Newton per millimeter square. And what is the stress? How much? What is the nature of the stress? It is tensile. I hope you have understood. This is a general analysis, general procedure to analyze compound bar or composite bar. And now when I take up the problem, it is only similar to, or I have to substitute all these values, and the problem, the first problem what you have with you, I shall read, or we shall together read it and make substitution in all this and make a sketch and solve the problem. Okay? So we shall read the problem loudly. Please read it along with me. This is a problem from January 2018. The problem is quite simple and very similar to the one what we have solved. Okay, a bar of brass. Okay, so instead of material 1 and 2, here what is the exact material that is given? A bar of brass 25 mm diameter is enclosed. This is inside. Now it is enclosed in a steel tube. Okay, a bar of brass 25 mm diameter is enclosed in a steel tube of 50 mm external diameter and 25 mm internal diameter. Okay, 25 mm internal diameter. Let me read it completely and then come back, and then if required I shall read it again. The bar and the tube. Okay, the bar, the inside one is a solid one, that is why it is being called as bar. The outside one is a hollow one, therefore it is being called as tube. The bar and the tube fastened means joined at the ends and are 1.5 meters long. Okay, the whole unit is 1.5 meters long. Find the stresses in the two materials when the temperature rises from 30 degrees centigrade to 80 degrees centigrade. That means this 1.5 meter is at 30 degrees Celsius. Okay, so let me draw now. Okay, quite simple. Very similar to the one which I had demonstrated just now. So inside is a brass. And I know that its length is 1.5 meters or 1.5 into 10 raised to 3 millimeter. This is the length of the bar. Okay, this is made of brass. Okay, what all information I have? I know its diameter. So 5 is 25 mm. The diameter of this is 25 mm and its length is 1.5 meter. And surrounding that you have steel. Okay, the steel is a hollow one. It is having inside diameter 25 so that this can be enclosed. And the outside diameter is 50 mm. So this diameter is 50 mm. 50 mm 5. This also is diameter. And the inside is 25 anyway. This is made of steel. This steel. Okay. And the temperature, when it is 1.5, that time the temperature is 30 degrees centigrade. Okay, find the stresses in the two materials when the temperature rises from 30 to 80. So delta T is 80 minus 30, which is equal to 50 degrees Celsius. 50 degrees centigrade. This is a change in the temperature. Okay, you have other informations. What are those? E steel 200. This is E steel. You can write it separately also. This is 200 gigapascal, that is nothing but 2 into 10 raised to 5 Newton per millimeter square. Okay, I hope you are familiar now and then you are able to write down straight away. Then alpha of steel. So alpha of steel, this also is given. This is 11.6 into 10 raised to minus 6 per degree Celsius. Okay, E brass. Okay, E of this, E, let me call it as E brass. That is equal to 1 into 10 raised to 5 Newton per millimeter square. And alpha of brass is more than that of steel. It is 18.7 into 10 raised to minus 6 per degree Celsius. Okay, instead of 1 and 2, we shall call now brass and steel. Brass and steel. Probably you can calculate what is the, which are required definitely. A brass, how much? Then you can calculate what is A steel, how much? This is pi by 4 into 25 square. This is so many millimeters square. Similarly, this is pi by 4 into 50 square minus 25 square. This is so many millimeters square. It is required. That you can calculate and keep it ready. Okay, everything is fine now. Okay, I can find out what is called as delta L of brass. Delta L of brass. How much is that? This is nothing but alpha brass, that is 18.7 into 10 raised to minus 6 into the length, that is nothing but 1.5 into 10 raised to 3 into delta T, which is nothing but 50. So to calculate this, this is so many millimeter alpha L brass. 1.4025. So since it is quite small, we shall go up to 4 decimal places. 1.4025 millimeter. On the same lines, can you calculate what is delta L of steel? This is 11.6 into 10 raised to minus 6 into 1.5 into 10 raised to 3 into the change in the temperature delta T 50, the same thing. So how much it is? 0.87. 0.87 millimeter. Okay. So now let me go back here. What may happen? Okay, the brass has increased along, has undergone a longer extension. So I am showing it. I want to write down the equation for easily to understand it. I am showing as if this is so high the length. How much is this? What is this? This length is delta L of brass. I shall substitute later on, which I know already. Okay, then what is delta L of steel? It is only 0.7, 0.87. This is smaller. So this is from here to here, delta L of steel. Okay, so now as we know that they are friends, they are going to have settled down somewhere So okay, the one which has undergone larger extension, that will compress, and the one which has undergone lesser expansion, that will further expand. So therefore, let me assume that this is the final one, final position. Say final. They undergo compromise and they settle here. Okay, so for their compromised position, so what should happen? The brass must undergo a compression. And what about the steel? The steel must undergo expansion. And both forces must be one and the same, and so that they cancel each other and the equilibrium condition is retained. So now, how much is this length? From here to here. This, how much is this? This is P into L divided by area of the brass into E of the brass. Because, sorry, it is not brass portion, it is steel portion. This expansion is from here to here. It is the expansion of the steel. It is P into L. They are same for both brass and steel. Then A of steel, then E of steel. It is basically PL divided by AE. That's the formula what I am using. And similarly, what is this portion? It is a compression of the brass, which is equal to PL divided by area of the brass into E of brass. Okay, now you are ready to write down the equation. What is that? Delta L BR. Delta L BR. I shall substitute now. Delta R, maybe once I shall write it. Delta L BR is equal to what? It is delta L ST plus P into L divided by AST into EST plus P into L divided by A brass into E brass. Okay, so what all things you know? You know 0.8, delta L BR, it is 1.4025, and I shall get delta L ST to the left hand side, it becomes minus 0.87. P is equal to, I shall take P outside, and I shall take L also outside and substitute that. And what is L? L is 1.5 into 10 raised to 3 into bracket. That is what PL I have taken outside. It is 1 upon AST EST. So 1 upon, what is AST? You have done it. You know what is the value. And you also know EST. Plus 1 upon, okay, A brass, E brass. That also you know. Okay, the whole thing is known. Then multiply to 1.5 into 10 raised to 3 and bring it to the left hand side and simplify here and then calculate what is the value of P. This is so many newtons. 14.88 kilonewton. Okay, into 10 raised to 3. Okay, you have this P. Once you have P, now what is quite simple. What is the sigma of brass? What is the stress in brass? How do you calculate? P divided by area of brass. Okay, so many Newton per millimeter square. And what is the nature of stress in brass? Look at the diagram here. It was here and it has been compressed, and therefore the stress is compressive. 30.32 compressive. And similarly, sigma steel P divided by AST. This also so many Newton per millimeter square, and this is the tensile in nature. 10.10. So much. Okay, so I thought of actually solving two problems. I hope you have understood now. and I don't mind. I hope I can compensate this in my next lecture or next class, and where I intend to do 2 instead of 2, I shall do 3 problems, and good day.